Okay guys, last time we were talking about the canonical forms. We saw how to go from a transfer function and take advantage of this to create the basically the flow diagram or phase variable state diagram. And from here it's very simple to go and find the state differential equations. So now let's move forward to this example in which we have a DC motor and we want to find the shaft velocity at the output. So what we're going to do at the very beginning is we're going to understand this transfer function or this block diagram. So this is an open system or an open loop system in which basically the motor has, here's our input signal and here is basically the velocity at the shaft. The motor is broken into three different transfer functions. One transfer function is basically the controller, the one that controls the velocity, the input signal, and basically applies a field voltage to the motor. Then we have a motor and load, and basically between these two transfer functions, we generate a current, and that current is applied to the motor, and finally the motor will produce a velocity at the shaft. So now let's understand what's going on or how we work this problem. So the first thing we need to do is we need to analyze each of the transfer functions individually. Okay, so here we have for the first transfer function, here we have the output, here we have the input. So the way we see it is here we have the input and here we have our output. Now in between these two we're gonna generate our input, basically we can call it the bubbles, the intermediate bubbles, or the state variables. So in this specific case, let me remove this. In this specific case, here we have our state variable x3 and here we have our integrator. So that means this bubble in here, it's x3 dot. So now we look at our transfer function and we start figuring out everything that needs to be done. So our transfer function, we have it in this way. We need to organize it a little bit. So let me erase everything so we can start clean. And our transfer function will look something like this. So if we expand all the terms, that'll be equal to 5s plus 5 over s plus 5. Okay, so then we multiply top and bottom by s to the power of minus 1. So this is going to be what? This is going to be 5 plus 5 s to the power of minus 1 divided by 1 plus 5 s to the power of minus 1. So from here what we see is that we have two forward paths and one back loop or one feedback loop. Okay, so we start from our feedback loop. Basically the feedback loop goes from our transfer function, our state variable, back into the integrator. So this has a gain of minus 5. Then we look at the forward paths. We have one path that should cross one of the integrators and had a gain of 5. So we go forward, cross the integrator, and the gain of 5. And finally, we have a path that should be skipping the integrator. So we have a path that skips the integrator. So what we're seeing here is basically everything that we have in the box. Let me draw a box really quick. Everything that we have in here represents our transfer function or the first block diagram. Then we look at the second one. We organize the second one, so it's going to be multiply top and bottom by s to the power of minus 1. So it's going to be s to the power of minus 1 over 1 plus 2 s to the power of minus 1. So we only have one forward path and one feedback loop. So what we have is one forward path and one feedback loop. And then finally, we have the last one that is going to be 6 s to the power of minus 1 over 1 plus 3 s to the power of minus 1. So going with that, basically we have the transfer function here. Now, now we're going to pick all our transfer functions, so or our state variables. So in this specific case, the author decided to make x2 equals to is, x1 equals to ys, and he decided to pick the next state variable as being x3. So from here, if we want to know what's the value of x3, basically the only thing we'll need to do is work out the math in here to find out the different things. For example, in this specific case, what's going to be basically x2. So in this case, if we look at it, x2 basically is I of t, x1 is equal to y of t, so that's not really that difficult. And then the next part will be x3. Okay, so let's start with u of s. So if I want u of s, this is going to be equal, so it's x3 propagating forward, so it's going to be 5x3. So then we jump whatever's on this bubble forward multiplied by 5. So on this bubble, what we are getting? We are receiving rs and we are receiving minus 5x3. So we're going to have plus 5rs minus 25x3. So now that we get it like this, we can say, okay, so u of s will be equal to, so it's going to be minus 20x3 plus 5 rs, okay? And from here I can solve for x3 and say x3 will be equal to, so it's going to be 1 over 20. So if we move it, so it's going to be 1 over 20. Well, let me change it a little bit, getting ahead of myself. So it's going to be 5 over 20 r of s minus 1 over 20 u of s. So we can simplify things up and we can say x3 will be equal to 1 over 4 rs minus 1 over 20 u of s. And from here the only thing we need to do is we need to take the inverse Laplace transform, and what we'll get is that x3 as a function of time will be equal to 1 over 4 r of t minus 1 over 20 u of t. And that will match basically the expression that we have here from the author. So this is a very simple way to look at it. And from here, once we get our state equations, the next step or the next thing we can do, we can obtain the state differential equation. Okay, so it's a very simple thing. We look at this and we said, okay, x1 is equal to y of t. So, oh well, we need the derivatives, not just the regular state variables. Okay, so this is x1 dot, this is x2 dot, and this is x3 dot. So we're going to find from our state variables that x1 dot will be equal to what? x1 dot will be equal to 6x2 minus 3x1. So we look at our matrix. So minus 3x1, 6x2, x2 dot will be equal to what? So it's going to be u of s minus 2x2. So we look here and we have basically what we just said. However, it's a little bit different here. It is saying, okay, u of s, it's putting it in terms of, well, our state differential equation is in terms of our inputs, our state variables and inputs. And here we have a problem because u of s, it is not our input. So the next thing we need to do, we can grab our state equation and we can say, okay, so previously we have that x3 will be equal to 1 over 4 r of s minus 1 over 20 u of s. If you remember, we solved this. Basically, we said that we can say u of s will be equal to 20x3 minus 5 r of s. So we can use that, substitute u of t here in this expression, and say x2 dot will be equal to what? So it's going to be u of s. So in this case, it's not u of s, but it's going to be 20x3 minus 5 r of s minus 2x2. So this is going to give us what? So it's going to be minus 2x2. So this is the minus 2 we have in here. Okay. Then we have 20x3. So we have minus 20x3. I have a sign that is missing somewhere. Seems like I'm missing a sign. Let me find it. So we have a minus 2x2. Then we have minus 20x3. But I still feel I'm not missing that minus 20. Oh yeah, I made it wrong in here. Let me fix this really quick. So this equation is not correct. So we have u of s will be equal to, so it's going to be multiplied by 20, so that's going to be 5r of s. Okay, and then it's going to be minus 20 x3. So now it's going to match. So now it's going to be 5r of s minus 20 x3 minus 2x2. So now I have, so it's going to be minus 20, and then we have 5r of s. Okay, and then we look at x3 dot, and x3 dot will be equal to what? So it's going to be minus 5x3 plus rs, and that's gonna be it. So it's gonna be minus 5x3 and the rs, and our output will be equal to what? Basically the output y of s, it's equal to x1. Okay, so this is what we have here. So you can see it was a process fairly simple, other than the little bit of a mistake that I had there on the little algebra problem, but in general it's fairly simple to find it. So now let's move forward to the last model we're going to cover, and that's what is called the decoupled response mode. So what we do is like finding the inverse Laplace transform. So what we do, we start with our transfer function, and we start a process of finding the partial fraction expansion or partial fraction decomposition. We find the coefficients, and what we're going to do, basically, we're going to say each of these will represent one forward path and one feedback loop on our flow diagram. So what we have is something like this. Basically, our input going to the output. We're going to have a connection of 1 in between. Then we're going to have our state variables in the middle. So we're going to have our state variables in the middle that we have x1, x2, and x3, and finally we have our output y of s. So what they're going to be connected, the output will be connected with different coefficients of our partial fraction decomposition, and then our feedback loops will be basically the poles or the roots of our polynomials in here. So this is very simple. Then if we go and build the state variable differential equation, what we get is basically something like this. A couple of things that we need to look at is that in this this is a diagonal canonical form, or that's how they call it. In this specific case, you can see that all the poles of our function, or the number -5, -2, and -3, they are part of our state variable differential equation, and it is required that all the poles need to be different. This is not basically what is called or known as the Jordan canonical form. So this covers basically, or this basically ends to some extent the different types of canonical forms that we use. Most of the time I'll ask you to do just the basic canonical form or this canonical form that we have here. I'll recommend you to make sure that you understand how to make these flow diagrams so you can be able to work with them and obtain the transfer functions and state variables from there. So now we're going to look into a typical problem for control systems in which we need to find, basically we have the inverted pendulum problem. In this problem, the whole idea is to apply a force to a cart. Okay, so we apply a force to a cart. We're assuming that the cart is on a surface that is frictionless, and on the top of a cart we have a mass attached by a rod. This rod is massless, and we have it attached to the rod, and the whole idea is to keep this mass balanced or vertical by applying force. So in other words, we need to apply either a force forward or a force backward in order to keep the mass on top balanced. So if the mass starts tilting to the right, we need to apply a force to the right to move the cart and apply a torque on that mass on the opposite direction. So we can counteract the torque from the gravitational force. So what we're going to do, we're going to work with what we have, with what we know so far, or basically this is a dynamics problem. So we start with the mass, and we're going to basically the mass will the gravitational force will apply a torque in this direction, and the displacement of the mass, or basically the force from the interaction or the torque on the mass, will go on this opposite direction. So in this case, if we look at the angle, basically if we find a triangle here we have our angle theta. So that means the force applied on this side of the mass that is due to the gravitational force, it is going to be LmG sine of theta. Now on this side, if we do the same thing and we find the angle, we're going to find that the angle is located here. This is going to be theta, and basically we're going to have here the force that is applied due to the torque. That is going to be Lm y dot double dot cosine of theta. So now that we have it like this, what we're going to be using, or how we're going to be working with, basically what we're going to do is we're going to use the equation that says that the sum of the torques should be equal to the derivative with respect to time of the angular momentum, or L. Okay, so in this specific case, because we're talking about basically a mass that we're going to be working here, we're going to use that the angular momentum of the mass, it is going to be equal to L, is going to be equal to I times theta dot, where I is going to be the moment of inertia. And in this specific case, the moment of inertia for a point mass it is going to be equal to I equals to m times L squared. So using this, basically, let's start with the little mass attached to the rod. So we have something like this. So on the summation of the forces, we have, let me do it in this way. So we're gonna have the sum of the force, or basically it is gonna be the torque. So Lm y double dot cosine of theta plus, so this is gonna be, let me just, this is gonna be negative because it's moving in to the left, plus Lmg sine of theta equal, let me put the equal right here at the bottom, this is gonna be the derivative with respect to time of the angular momentum of this mass, that in this case is gonna be what? So it's gonna be I theta dot. So working this equation, basically what I get is when I make the derivative of this is going to be I theta double dot. Now from here, what I'm going to make a little bit of an assumption. In this specific case, for the system to be linear, we need to assume that theta is small. So now if theta is small, that means we can say that sine of theta is going to be approximately equal to theta, and the cosine of theta will be approximately equal, let me erase that, for some reason my pad is acting up, and the cosine of theta is approximately equal to 1. So in that case, basically this becomes a 1, and this becomes theta, so we have the expression from this side. So we have, let me rearrange things a little bit. So everything gets rearranged. So we basically transfer these to the other side. We substitute the value for the moment of inertia. So what we get is the expression right here at the bottom. So that's for the little mass on the rod. Now for the cart, we're going to have something similar, but now we're going to look at the torque at this moment. Basically the torque that it's opposing, or depending on how the cart is moving, is going to be on a different direction. So we're looking at the tangential force, or basically the force applied to the cart. So in this specific case, if the mass is pushing in one direction, according to Newton's law, we're gonna be seeing a force in the opposite direction being transferred. So in this specific case, if the torque is this one, we're gonna have a tangential torque in this direction. Okay, so that means we're gonna have the torque plus the mass times the acceleration. Hold on, I think something, I got it wrong real quick. Actually, the torque is going on the opposite direction. So the mass times the acceleration plus the torque minus the force applied to the cart. So from here we define our state variables x1, x2, and x3, and x4. So we substitute those on our state variables, so we get something like this. So from here, we can easily find what is going to be x1 and x2. So we can see that x1 dot, it is going to be equal to x2, x3 dot will be equal to x4, and then we go into x2 dot will be equal to this expression, and x4 will be equal to this expression. So mainly what we did is we defined, let me look carefully, I don't want to mess up with my notes. So in this case, x1 will be equal to y, and x3 it's equal to theta. So using this, I substitute these state variables back into our differential equation, giving me basically the expression for, or the state variables for these. So using these state variables, I can come up with my state, or basically my matrix that will allow me to simulate. So my matrix A for my state equations will be given like this, and my matrix B for my state equations will be given in this form. So now that we have it like this, it will be a matter of opening something like MATLAB and grabbing the basically using the commands to simulate the system. Now in this specific case, I decided not to simulate the system in MATLAB because the only thing that I'm going to simulate, it is just going to be either the mass dropping in one direction, because I will need to actively control the force u of t. And in order to actively control the force u of t, I'll need to include a feedback system to my, or a control system to my MATLAB code. And at this moment, we haven't covered that. So in this case, I will not go forward and simulate it in MATLAB. Now, let's learn a little bit more about the another technique. Let's say we have the state equations, but now from the state equations, we want to find out the transfer function. So how we do it? Assume we start with state equations written in this way. So this is basically a linear algebra equation. We have matrices and vectors in here. So using the Laplace transform, we obtain this. So basically we made the Laplace transform of the matrix, the Laplace transform of this, Laplace transform, and basically we ended up with this expression. Now that we have it in this way, we need to play around with it. Basically we're gonna move everything that depends on x of s in one direction, and everything that depends on u of s on the other direction. The same, we'll do it for this side of the equation. So, working with this, we move everything around, so now we have our linear algebra equation in this way. So next step is we're going to define what we call our state transition matrix in this way. So our state transition matrix will be defined as S times the identity matrix minus the matrix A, all of that inverse, or the inverse of that matrix. So what we are saying is that when we solve for x of s, basically x of s will be equal to the state transition matrix times v times u of s. Now using this concept, we can substitute that expression, or basically the value of x of s, back into our equation of y of s. So finally, what we get is this equation for y of s that says that if we know the value of a matrix D, the value of a matrix V, the state transition matrix, and the value of a matrix or the vector C, we're going to be able to find our output y. But we are not looking for the output, but the transfer function. So we divide everything by u of s, or our input, and we finally find out that if we know all these matrices and vectors, we can find out the transfer function fairly simple, just by multiplying C times the state transition matrix plus B and then add D. So as an example, let's work with the RLC circuit that we have been working for a while now. So we know from previous knowledge or from previous problems that the state transition, or not the state transition, the state equation for the RLC circuit is given like this, where this represents our matrix A, this represents our matrix B, or our vector B, this represents the vector C, and in this case we don't have a vector D. So what we're going to do, first we're going to need to find our transfer function. For that, we'll need to find first our state transition matrix. So we know that the state transition matrix is given by this expression, okay, that says the state transition matrix is equal to S times the identity matrix minus A, inverse of that. So let's start with the very beginning. So we said, okay, let's start by saying S times the identity matrix minus the matrix A. So this is equal to what? So this is a 2 by 2 matrix. So basically we're talking about the identity matrix by S will give us S, 0, 0, and S minus our matrix A, that in this case is going to be 0 minus 1 over C, 1 over L, minus R over L. Okay? So now that we have done this, we can subtract one from the other. So this is going to be equal to S, 1 over C, minus 1 over L, and then S plus R over L. So now we have that. So the next thing we need to do, we need to find the inverse of this matrix. There are different ways to do it. One of them is finding, for example, the determinant, or Kramer's rule. So we find the state transition matrix phi of S. It's equal to S times the identity matrix minus the matrix A. This should be matrix. All of this inverse. So what we find is basically this is going to be equal to 1 over delta of S times, by using Kramer's rule, S plus R over L minus 1 over C, 1 over L, and then S. So from here, basically we define this as basically the determinant of our matrix. So our determinant of the matrix delta S, it's equal to S squared plus R over L of times S plus 1 over L times C. So now that we have our state transition matrix, the next thing we need to do is just find a transfer function. So we use this expression to find our transfer function. So it's going to be C times the state transition matrix times V minus plus E. So in this specific case, our transfer function G of S will be equal to, so the matrix C, or the vector C, 0 times R, times my state transition matrix, that is going to be 1 over delta of S, times S plus R over L, 1 over L, minus 1 over C, times and then S, multiplied by my vector C, that is what? It is going to be 1 over C, and then 0. So when I multiply this whole thing, what I come up with is the following. So it's going to be R over L times C divided by S squared plus R over L times S plus 1 over L times C. And if we remember from our previous lectures, this is basically the transfer function of our RLC circuit. So guys, I'm not gonna cover more because that will mean going into a little bit of a different topic, and I don't want to overwhelm you with a video with a lot of detail that we haven't covered too much about it. So what I'll say right now is, look at these problems. I'll recommend you to go and look carefully at the two different things that we cover. So how to work this problem with the DC motor, how to work the flow diagram and obtain the state variable differential equation, and how to work with the inverted pendulum. I'll recommend you to go and review your concepts on torque, how torque applies in this case, and verify that what we get is exactly these things. So I'll see you the next class. Have a good day.